basic sound system. Even a simple sound system has several components to amplify the sound: microphones, mixing consoles, equalizers, power amplifiers, and loudspeakers. A microphone picks up or captures various sounds and converts that acoustical energy into a tiny electrical voltage that we call an audio signal. The voltage from that microphone is too small to drive a loudspeaker directly. First, we need to send that signal through other equipment in order to boost the strength of that audio signal. We use a microphone cable to carry that electrical signal from the microphone to a sound mixing console. We plug one end of that cable into the mic and the other into the mic input at the sound console. Each microphone input relates to an input channel on the console. Depending on the size of your music group, you may have just one or two mics in use at one time, or you may have several. The more mics you will need to use, of course, the more input channels your console will need. The sound console allows us to balance or blend those sounds into a musical mix that is pleasing to listen to. We often call the console a mixer or a mixing console for that reason. The main output of any mixing console must be sent or fed to the main loudspeakers so that our listeners can hear the sound. Here again, the electrical signal required to make the loudspeakers move so we can hear that sound is way more than the console output can deliver on its own. So first we need to take another audio cable, plug it into the output of the console, and plug the other end into the input of the power amp. The power amp does what its name implies. It amplifies or raises the electrical signal enough to move the speaker cone on that loudspeaker. We use physically larger wires called speaker cables to deliver that electrical energy from the power amp to the loudspeakers. That describes the main path through any sound system. It doesn't matter if the system is very simple with one mic and a mixer and a couple of self-powered speakers, or if it involves several microphones plugged into a large console, feeding a very elaborate loudspeaker system in a large room. Any such sound system will have the same components, just some more than others. As we go through this study of a sound system, this would be a good time for you to take stock of the equipment that comprises yours. Can you name the manufacturer and model of the mixing console, or the power amps, or the loudspeakers? Connecting the system components. So how do we connect one device in the system to the next? Realize that the audio signal remains an electrical signal all the way from the microphone through to the loudspeakers. But we use different types of cables between the various components so the audio signal is properly carried from one device to the next. For example, the output of an electric guitar or a keyboard typically uses a relatively short cable called a patch cord or a guitar cable to connect the instrument to the guitar amp or to a direct box. It has a single copper conductor wrapped by a copper shield with a 1/4 inch phone plug connector on each end. We call this an unbalanced cable. Such cables are fine to use in this instance, although they are of limited use because longer cable lengths can degrade the frequency response and the quality of sound. By comparison, a mic cable has two copper conductors that are twisted around each other and wrapped by a shield, with a 3-pin XLR connector on each end. That shield helps to lessen the interference from electric fields like radio transmissions or the energy given off by fluorescent lights. The mic inputs of the console have circuitry that takes advantage of the two conductors, allowing very long cable lengths without any degradation of the audio signal. We call this a balanced cable. We can also use a balanced audio cable, two conductors wrapped by a shield, to connect the output of our console to the input of a power amplifier. At the output of the power amp, we use what we call a speaker cable, which contains two large gauge conductors to make the connection from the amp to the loudspeaker. We prefer speaker cables where those two conductors are twisted together the full length of the cable. And in general, the larger the gauge of copper wire, the better. With speaker cables, there is no need for a shield. To summarize, we use unbalanced cables to connect guitars and keyboards and even CD players to our sound system. We use balanced cables to connect the microphones to the console and to connect the console to the power amp. And then we use speaker cables to connect the power amp to the loudspeakers. Could one use a speaker cable to connect an electric guitar to the sound system? Well, an audio signal might pass, but the sound quality can suffer. We explore the reasons why and further clarify terms like unbalanced and balanced in our Level 1 class. Microphones. A microphone can be used to pick up one voice or instrument, or it can be used to pick up a large group like a choir. Aim the microphone like it would a flashlight to pick up the sound you want. If the group is too large to properly capture with just one mic, if you will, to fully light with just one flashlight, then we might need to use 2 or more mics to pick them up. But be careful, using too many mics is a common mistake. In most cases, the fewer the mics used, the better the sound quality will be. Microphones are available in different construction types, pickup patterns, and of course price ranges. To get the most from the microphones you have available, you need to know at a minimum what their polar pattern is, so omnidirectional, cardioid, supercardioid, hypercardioid, or bidirectional, and whether they are dynamic, condenser, or ribbon. Dynamic mics are the most common type. Their construction comprises a dome-shaped piece of mylar suspended above a magnet assembly. A very long piece of copper wire is wound in a circle, edge to edge, and glued to the back of that mylar diaphragm. When assembled, that coil of wire rests in a magnetic air gap. As sound waves strike that diaphragm, it wiggles back and forth. That coil of wire goes for a free ride in that magnetic air gap. God's laws of physics says that whenever that condition exists, an electrical signal will be induced to flow in that wire. The 2 ends of that long piece of wire ultimately connect to pins 2 and 3 of an XLR connector built into the housing of the microphone. In a nutshell, that is how the dynamic microphone converts the acoustical energy striking the diaphragm into an electrical signal. A ribbon mic works in very much the same way. In this case, its diaphragm is actually a thin strip of metal called a ribbon and stretched between 2 fixed posts. The ribbon is laying in a magnetic field, and when the sound waves strike that ribbon, it converts that acoustical energy into an electrical signal, which then appears on pins 2 and 3 of the XLR connector built into the mic. The condenser mic works a little bit differently. Here the diaphragm is a thin metallized piece of mylar. It's metallized so that it can serve as one plate of a capacitor, and is positioned very closely to what is called the fixed back plate. Together they make up the 2 plates of a capacitor. A short wire connects each plate to an electrical circuit called a preamp built into the housing of the mic. When sound waves strike the diaphragm, it wiggles back and forth, changing the distance between it and the fixed back plate. And God's laws of physics says that when that condition exists, an electrical signal will flow from the capacitor through the preamp and then to the XLR connector built into the mic. So now that you're familiar with the 3 most common types of microphone construction, let's talk about polar patterns and how we can use them for our benefit. There are actually 5 classic polar patterns to choose from: the omnidirectional, cardioid, supercardioid, hypercardioid, and the bidirectional pickup. And we can add to that the hemispherical pattern, courtesy of the pressure zone mic, also known as the PZM. The Omni mic is equally sensitive to sounds arriving from anywhere around it. It's easier to build than the directional mics and has fewer problems associated with it. However, in live sound applications, that anywhere acceptance angle can make it more prone to feedback. Having said that, most ear-worn mics use an Omni capsule, and it works in that application because we're placing the mic within an inch or so of the sound source we're trying to pick up, the person's voice. For much better gain before feedback and flexibility in placement, we turn to the cardioid microphone. Switching from an Omni mic to a cardioid mic will improve our gain before feedback stability, as well as our direct to ambient sound ratio, meaning less pickup of the sounds we don't want, by as much as 70%. The most common microphone we find in churches is a dynamic cardioid, like the Shure SM58 pictured here. It's overlaid on a polar response graph to illustrate where its pickup is the strongest and where it's designed to attenuate the sounds. Note that the pickup is actually in 3 dimensions. In this case, the best pickup is achieved speaking directly into the front of the mic, called 0 degrees on axis, and its maximum rejection point is 180 degrees off axis. The cardioid mic has an acceptance angle of 131 degrees. In other words, as long as the sound source you're picking up with that mic, for example, a vocalist, is within 65 degrees of the center of the mic, your listeners will hear no loss in level or sound quality. That is why you'll find cardioid mics used in most applications for live sound, followed by supercardioid mics, in particular for handheld vocals. On a side note, let's say that you're miking a vocal trio, and you discover that one of the 3 vocalists has a weaker voice than the others. Place the weaker vocalist at 0 degrees on axis. and the other two vocalists on each side of the mic. That will help them blend more easily with the other two vocalists. The supercardioid pickup pattern has an even tighter acceptance angle, 115 degrees. When used for a vocalist, it is intended to be used as a handheld mic or on a stand very close to the vocalist. It could be used by two vocalists, but typically is just a one person per mic. The reason to move from a cardioid mic to a supercardioid mic is further improvement in gain before feedback. The same can be said of the hypercardioid mic. Its tighter acceptance angle yields even better gain before feedback. You will notice that each time we tighten the acceptance angle, the pattern creates a rear pickup lobe. In other words, there's no free lunch. That lobe is a trade-off of creating the tighter pickup pattern. On a side note, compare the polar response of each of those 5 patterns, paying close attention to the location of the maximum rejection points. If we want the best gain before feedback from a microphone fed to the stage monitors, we want to position the mic so that its maximum rejection point is aiming at the monitor. So with the cardioid mic, we simply aim the back of the mic at the monitor. But notice with a supercardioid mic, the maximum rejection point is off to the side at 126 degrees. And in fact, there's a small pickup lobe at 180 degrees. So aiming the supercardioid mic with the back pointing at the monitor would actually be tempting feedback. Instead, we adjust the mic or the monitor to align the monitor and the mic's maximum rejection point. That's easier than it probably sounds, and we encourage you to keep it in mind when placing mics on the platform. By the way, the same condition exists for the hypercardioid mic. And yet another side note, not to confuse the issue, but how about we take this up another notch? Just as important, but not as obvious, is when we want to use our knowledge of the polar pattern to lessen the pickup of an instrument in a nearby mic. That sounds confusing, I know, but bear with me. Let's say that I'm playing acoustic guitar, and there's a mic placed near me to pick up my guitar. And let's say that you're playing grand piano nearby with a mic on the piano. Ideally, we want the mic on the piano to pick up just the piano. And we want the mic for the guitar to pick up just the acoustic guitar. So here's one of those hard-won secrets that finally dawned on me one day, using the polar pattern intentionally. If that mic on my acoustic guitar is picking up a lot of piano, how about if I just rotate my position and the mic so that the back of the mic, the maximum rejection point, is aiming at that piano? Problem solved. My guitar mic will now attenuate the sound of the piano and still have great pickup of the guitar. Now, it won't make the piano disappear. It's still going to hear some of the piano, especially at lower notes. Think wavelength. But that minor adjustment to aiming the mic just cleaned up the musical mix a great deal. Finally, we have the bidirectional pickup pattern, giving us 2 equal pickup lobes, one on each side of the diaphragm. You've probably seen music videos where 2 vocalists facing each other with a mic in between them. That's most likely a bidirectional mic. They're great for certain applications, but they cost more, and their use is limited, so they're not nearly as common. Understanding mic technique, how to choose the best mic and where to place it, is discussed at length in our Level 1 CSPC class and covered in even greater depth in our Level 2 class called How to Get the Sounds. Mic technique combines art and science and is something that one can study for their entire career. Wireless microphones. Wireless mics can offer much needed freedom on the platform for the person using them. Manufacturers have done a good job of making them very easy to use. There are just a handful of points to remember in using them. A majority of wireless mic receivers are what we call diversity receivers. They actually have 2 antennas attached to a circuit that compares the strength of the RF transmission from the mic at the platform. It figures out which of the 2 antennas is receiving the strongest RF signal at a moment's notice and uses that signal to pass on the audio to the receiver. The system does this silently in the background. If you're experiencing any dropouts of the RF signal, check to make sure that you have line of sight between the antennas and the transmitters on the platform and the receiving antennas. Now, if you have multiple wireless system receivers stacked up on the ledge in front of your console, you're asking for trouble. Placing antennas so closely together can create RF interference with the good channel. In fact, the Shure website recommends that antennas operating in the 400 MHz range be separated by at least 10 inches to as much as 30 inches to minimize interference. As great as it is to have wireless mics to use, they're not without their problems. The question needs to be asked, how important is that need really? Consider that a cabled mic will often sound better than its wireless version, And of course, the cabled version costs a fraction of what the wireless mic costs. Add to that discussion the concern in the US that available frequency range that we are allowed to operate continues to shrink. Starting in July 2020, the primary frequency range that UHF wireless systems will be allowed to operate in will be between 470 MHz and 608 MHz. We totally understand the benefits of using wireless mic, and in many cases, it is in fact the best solution. We encourage you to carefully weigh the costs versus the benefits as you decide which mics need to be wireless versus which mics can be cabled mics. Mixing consoles. As I mentioned earlier, the sound console allows us to balance or blend those sounds into a musical mix that is pleasing to listen to. Bringing each voice and instrument on the platform into the console on individual channels allows the operator tremendous control over the balance. It also makes the process more complex. Consider these scenarios. Let's say that we're miking a vocal ensemble of 8 vocalists. We could pick up the entire group with one mic and let them blend themselves. Or we could let groups of 2 or 3 vocalists share a mic. Or we could simply hand each vocalist their own microphone. Sometimes it helps to use fewer inputs and let people blend themselves. The trade-off is that more mics means more inputs on the consoles, and consoles with more inputs cost more. The operator listens carefully to the relationship between the lead vocal and the backing vocals, how they balance with the musical instruments, and makes adjustments as needed to maintain that musical balance. The console is also where we establish the best gain structure for each input channel, and in turn for the entire sound system. Why do I mention such a technical and potentially confusing point right at the start of this topic? Because establishing proper gain structure ensures that the sound system will operate quietly, with no hiss and no distortion. If you experience either of those symptoms with your sound system, read carefully what I'm about to share with you. So here we have a picture of a channel fader. Note the position of the fader cap. Each manufacturer will indicate on the console silkscreen their recommended nominal setting for the faders, marking it with a 0 or a grayed area or in some other way. Starting with the faders at 0 helps you establish a quiet gain structure for each channel. That 0 setting is also the best location to start your mix, and here's why. Notice that a 1/2 inch movement of the fader up near that 0 will make about a 5 dB change in the level. By comparison, if we have the fader positioned down near that minus 30 dB position, a 1/2 inch move there will yield a 10 dB change or more in level. Creating your mix with most of the faders up around that 0 mark will ensure that your fader moves are smooth and barely noticed. If you have several faders down around minus 30 and you adjust them there, your audience is going to hear those changes. I'm not at all saying that you must leave the faders at that 0 mark, but in general you'll find that keeping your individual channel faders within roughly +5 and -10 of that 0 mark will work best. If you find that 1 or 2 of your faders are always down at that lower setting, it's likely a sign that the mic trim or gain of that channel needs to be turned down so you can then move the fader back up. Likewise, if you see that you often have trouble getting 1 or 2 channels loud enough in the mix, it's a sign that you should turn up the mic trim on those channels. Your goal, the condition you want to see, is whenever the music team is playing a big, strong, powerful song, you should regularly see the main output meters of the console cresting around 0 VU. It's okay for them to spill into the area above 0 VU and to ride below that point, but fairly regularly we want to see the music peaks at around 0 VU. Once the gain structure is set, we can make adjustments as needed to refine the sound character of those individual channels. Controls on the console also allow the operator to refine the sound character of the various vocals and instruments. For example, if the sound of one channel seems bassy or boomy, we can use the channel EQ or equalizer on that channel to reduce the low frequencies so it sounds more natural. We need to make that evaluation of tonal character for every single musical instrument and voice coming into this console. I have worked with a lot of very talented vocalists over the years. It's rare, but occasionally we'll encounter vocalists whose voice is so good that literally making EQ adjustments on their voice would be a mistake. Put a great quality mic in front of them, add a high-pass filter to get rid of any unwanted low frequencies, and move on to the next channel. It's more common to hear a voice for an instrument like a piano or acoustic guitar that sounds good on its own, but there may be a resonance here or there or a peak to the sound that deserves special care to refine it. The mistake that most beginning sound techs make is to go too far with the channel EQ. Typically, a change of 2 dB or 3 dB is all we need to smooth out the sound of that channel. You may discover that it only needs some minor adjustments on 2 or 3 EQ bands, and then it sounds fine. And if so, leave it alone and move on. Don't chase your tail with the EQ. Our ultimate goal is to create a balanced musical mix that allows the listener to hear each and every element clearly. A great way to start learning about how to build a musical mix is to do a lot of analytical listening. Sit down and listen carefully to some of your favorite songs and analyze each mix. How strong is the lead vocal compared to the backing vocals? And relative to all the musical instruments? Can you hear each instrument and each harmony part clearly? Creating a great musical mix requires knowledge of the technical issues that we've covered in this study, along with an understanding of the musical performance and sensitivity to the Holy Spirit. A good sound tech does not necessarily need to be a capable musician, although it does help, but they do need to have a love for music. System equalizers and digital signal processors. We mentioned above that the main output of the mixing console goes to the power amp that then drives the loudspeakers. In most sound systems, we connect another device in the signal chain. We take the console output and first feed it to an equalizer, and then to the power amplifier. Why add the system equalizer? We want our loudspeakers to have a smooth frequency response. Not only does that help our overall music mix sound better, but it also helps us minimize issues like feedback. The reality is that most loudspeakers are far from smooth, let alone flat. So we insert an equalizer in the signal path, which we can use to smooth out the frequency response of the loudspeakers. It's unlikely that we'll ever achieve a ruler flat response of each loudspeaker, but careful adjustments can definitely improve the sound character. A digital signal processor, also known as a DSP, is a computer-controlled device that includes several equalizers along with other elements like limiters and signal delays. Now, with a simple sound system, one might be fine with a single equalizer installed in the equipment rack next to the power amp. In a more complex sound system, especially one with several loudspeakers, it's common for us to want an individual equalizer, limiter, signal delay, and other components for each of the loudspeaker feeds. That would require a lot of rack space, not to mention significant financial investment. By comparison, a single DSP can provide multiple inputs and outputs, each with its own collection of EQs, limiters, delays, and so on, all in a rack mount unit that may only require 1 or 2 rack spaces. Having separate control of each individual loudspeaker allows us to coordinate them so they will work as a system rather than several loudspeakers that happen to be located in the same room. Power amps and loudspeakers. Loudspeakers have large drivers in them, with funny names like woofer or tweeter or compression driver, and those are used to push the air so we hear the reinforced sounds. Those large woofers have heavy paper cones, which take a lot of electrical energy to move them back and forth. In fact, pushing the air at low frequencies takes quite a bit more energy than pushing the air at high frequencies. The power amp provides that electrical energy, and its output is measured in watts. For example, the woofer in a loudspeaker might require 300 watts to drive it to full output, while the high-frequency driver in the same loudspeaker might only require 50 watts to drive it to full output. We discuss in the main class how big of a power amplifier is needed for any system, and we clarify how to make sure that the overall gain structure of your sound system is set properly. When it comes to power amps, simply put, the more power the better, within the capabilities of your loudspeakers, of course. Now, there is a common misunderstanding that the knobs on a power amplifier always need to be set wide open. The misunderstanding is what those knobs do. The reality is that the power amp itself is always operating at full output. Those knobs are only adjusting the input sensitivity of the power amp. They determine how much voltage is required from the console to drive the power amp to its full output. So the question remains, where should those controls on the amplifier be set? And I'm going to reveal a trade secret that even many sound techs are not aware of. Allow me to backtrack for just a moment. I mentioned console gain structure a little while ago. The condition you want to see is whenever the music team is playing a big, strong, powerful song, you should regularly see the main output meters of the console cresting at around 0 VU. It's okay for them to spill into the area above the 0, okay to ride below that line, but fairly regularly we want to see the music peaks at around 0 VU. Now we turn on our power amp, and literally, this is the trade secret. We simply turn up the power amp until it's loud enough for our tastes. That's it. Yes, I know it sounds too simplistic, but that is proper gain structure. And with a simple sound system, with just a couple of loudspeakers, that works perfectly every time. However, for a more complex sound system with several loudspeakers, it might be that the sensitivity controls on each of several power amps need to be set at different levels. And that poses a problem. Number one, how are we going to remember those settings? And number two, how possible is it that someone might get their hands on the equipment and make unauthorized adjustments to those power amp settings? So on larger systems, we can use the output controls of a DSP to lock those settings into memory. We go ahead and turn up the power amp controls to wide open, and then back at the DSP, connected between the console and the power amp, we throttle those output controls back to a position where we can balance the sound level of all the loudspeakers in a way that they work as a system rather than a number of individual loudspeakers. Choosing the best loudspeaker for a given application is a task that should not be taken lightly. The process involves methodical, scientific study, coupled with art and first-hand listening experience. Only then can one know and understand specifically where to place a certain loudspeaker and how to aim it to achieve the desired results. Smooth, even sound coverage for all listeners. Polar patterns, sensitivity, polarity, phase cancellations, and other details are all covered in the main Church Sound Bootcamp class. Terms, abbreviations, and acronyms. As with any industry, it's common to use terms, abbreviations, and acronyms to make communication more efficient. And of course, if those terms are new to you, they actually slow down the communication. So here's a short list of common terms and abbreviations used in the audio industry. FOH means front of house, which, depending on the conversation, refers to either the main loudspeaker system covering the congregation or the location of the mixing desk where that portion of the sound system is controlled from. You may find that the terms FOH, sound booth, and production booth are used interchangeably. EQ is, of course, the equalizer section on each input channel. Mute is another term for the on-off switch on each channel of a console. PFL and AFL stand for pre-fade listen and after-fade listen. Some manufacturers label this button as solo. Pressing the button feeds the audio signal on that channel to the headphone output, allowing the operator to hear just that channel without affecting the rest of the mixes. The astute reader will realize that pressing the PFL button allows one to hear the audio signal on that channel without having the channel fader up, which can be a tremendous troubleshooting advantage. When we say aux or aux send, we're talking about a separate, independent mix of the inputs on the audio console. The aux send is typically used to send a mix of the signals to a stage monitor or to an effects device to add reverb. DI stands for direct inject, meaning that we plug the electronic instruments like a bass guitar or keyboard into the DI, which then carries that audio signal directly to the console via mic cable. It's also known as a direct box. RTA stands for real-time analyzer, a common audio measurement device that displays the sound energy present in discrete frequency bands. A simple sound level meter only shows the overall sound level being measured, while an RTA displays the contribution of individual frequency bands that make up that overall sound level. AVL, of course, stands for audio, video, and lighting. You might hire a consultant to design the AVL systems for your new worship center, in which case that consultant will have experience with the design of each of those types of systems. And an AVL system integrator has crews that are experienced with installing all three types of systems. So what's next? Are you ready to dig deeper? We trust that you have enjoyed this brief study of audio basics. And if you're brand new to audio, we encourage you to review each module again until you're fully comfortable with the concepts and the terms. Please feel free to contact us directly with any questions about what you've learned here. Be blessed, This is Kurt Typley for Church Sound Boot Camp.